So welcome to lecture 2 of machine learning for the working mathematician. So my name's Joel, by the way. So in this lecture, we're going to go into a little bit about neural networks, just like a recap of last week, then talk about the universality of neural networks. This is basically some theorem that says that they can approximate any function that you'd want them to approximate. And then we'll talk about one of the big applications of neural networks, which is to image processing, because it's one of the wild success stories. And it also, we can learn a lot from it if we want to apply machine learning to maths. So a little bit of admin first. So we've now just put up an online discussion board. So there's a link to it on the website. You can go and create an account. And the intention of this is to be able to follow on discussion after the lectures. But if you have any unanswered questions after the lectures, or you want to comment on the lectures or on the workshops and so on, one note is that it seems to play badly with the spam filter at UCID. So you might want to sign up using a different email address. And then this is the slide that we're going to show at the start of every lecture. Right. So the first seminar principle is that we want all of your questions, remarks, and explanations during the lecture. Right. So don't hang on to them until after the lecture. Just feel free to interrupt. We schedule enough content to fit into 90 minutes instead of 2 hours so that we can be interrupted. Number 2, this is a learning seminar. So me, Geordie, and Georg are all learning just the same as all of you. We are by no means experts, so call us out if something looks wrong or if you know more about something. And the third one is we love examples. More examples are better, and we'll show some of those. A bit of a recap from last week. Last week, we went over the whole idea of machine learning. And in this lecture, I'm going to focus just on the neural network parts. So neural networks were made out of these things called perceptrons, or some people call them synapses or computational units. And what this is it's basically a linear function, which means an affine function, followed by something nonlinear. So how this perceptron works is it has some parameters in here, which are these weights. And then this last one, which is a bias, that's the affine part. And what it outputs is essentially just the affine combination of those things with its inputs. But it wraps them in some kind of nonlinear function. So these nonlinear functions are normally sigmoidal, which kind of means they look like 0, towards minus infinity and 1 towards positive infinity. This ReLU that we're using, you'll notice, doesn't do that. But it's very easy to build a sigmoidal function out of this ReLU. You just sort of shift it along a bit and subtract 1. And the activation function, which we're using this ReLU for, is sort of part of the structure of the perceptron. So we fix that ahead of time. And whenever we're trying to train this perceptron, all we're doing is training these purple numbers here. So that's what training the network means. It just means fiddling with the purple numbers until you get a better result than you had before. Right, and now we've got some terminology. So these perceptrons get stacked into layers, and each of these layers is called a width. So in this network down here, this layer here might have 20 perceptrons, and so we'd say that layer has width 20. All of these layers that are stacked vertically, or at least we draw them stacked vertically, get composed into a chain. That's called the depth of the network. And then some other things. So the structure of the network is the overall shape. So, how many layers you have, how many perceptrons you have, what your input and output space is, and the choice of activation function. Then parameters, I've tried to keep writing in purple, are these things that you train the network to do. So once you fix the structure, you initialize the parameters somehow, and then you train them. You tweak these parameters until the function seems to approximate what you want. And then there's this other term you might see floating around called hyperparameters. And these are kind of everything that a human might specify. So the structure of the network would be a hyperparameter. The exact method of training would be a hyperparameter. The variables used during training, what kind of data sets you show to it during training, all of these are called hyperparameters. And just to make sure you know what's going on, a typical depth 2 network looks like this. So this section here is called a hidden layer. They're hidden because they're not inputs and outputs and you can't see them. So this one has 2 hidden layers, which are these 2 parts in the middle, and then an output layer. And by convention, the output layer doesn't have this nonlinear part. But you can always apply that just after running the network or something. And if you want to count the parameters, to make sure that you understand what's happening, these are the numbers that you get. So, A is a 200 by 20 matrix, and B is a vector of length 20. The question is, why is the last layer missing the nonlinear function? And yeah, I think it's because you want to allow negative outputs as well. For example, in a classification problem, the kind of units of output are called logits. They're like some kind of unnormalized log probabilities. And so we kind of want to allow these things to be negative. The question was, how many perceptrons are there in the first layer? So there's 20 perceptrons in the first layer. So the sigma here, you should imagine it applying like component-wise to the vector that comes out. Right, so like ax plus b is a vector, and then the sigma, I'm just applying sigma to every element of that vector. The same sigma, yep. I'm sure you could cook up a network where you applied different sigmas, but normally it's the same. Right, so in the spirit of number 3, there's this excellent visualization through which you can have a look at a neural network. So this is called playground.tensorflow.org. So TensorFlow is a machine learning toolkit made by Python. It's very similar to PyTorch. You can do the same kind of stuff with it. But this little app here doesn't actually use TensorFlow. It really just uses a neural network as I've just described it to you. Right, if you have some programming knowledge, you could take what was on that previous slide and then make something that runs a neural network. And with a bit more thinking, you could make something that does all of the back differentiation and stuff. And this is exactly what this is. So this is quite interesting to play around with. So this is one hidden layer network. And what it's trying to do is classify these points on the right into blue and orange. And it's basically trying to output 1 or -1 to each of these points. So there's different activation functions we can use. So I'm going to use a ReLU, and you can just play this and see how it goes. And you can see this network evolving over time. So these epochs up here are kind of evolutions of the network. So in each epoch, they run some test data through it, measure the loss. We're using this loss function that we talked about. And then they use backpropagation to do gradient descent. And they've changed the network, and then they do it again at the next epoch. So you can see these things converging. Right, and if you reset it and run it again, you might get a different shape. And so you can see that this network seems pretty sensitive to the initial conditions, right? If they're like a little bit different, you get a different shape out the other end. And yeah, I'd really encourage you to just have a play with this. If you increase the number of neurons or perceptrons or whatever, things tend to converge a bit faster. I interpret this based on the idea that if you have more space, there's kind of more places to go during a gradient descent. You might not get stuck so much. Yeah.
Is the density of the connection reflecting the weight strength?
Yeah, that's right. So the if you're on the computer, you can mouse over these, but I can't on my iPad. If you mouse over them, it will show you the actual weight. But I think like blue, like thick blue is a strong positive number, thick orange is a strong negative number, and then the transparent ones are towards 0. And these little boxes on the bottom left of the neurons are the biases. Thanks, Jody. So, you can see, so this is running the same example that was in the workshop last week of just using like a very simple network to try to classify something as either in or out of a circle. So you can probably guess that if I go down to 2 neurons, this is going to go poorly. And this is basically because what you get out of this is like a fairly simple piecewise linear function. You just don't have enough pieces to approximate a circle very well. But one thing Jordy also mentioned is that you can apply these nonlinear transformations to your input. Right, so here I'm inputting the x coordinate and the y coordinate, but instead I could input the x squared coordinate and the y squared coordinate. And now theoretically, this neuron has enough information to calculate distance. There we go. So kind of the old mode of machine learning is to find these nonlinear transformations on the left that make your linear classifier, this one neuron, work very well. And the point of deep learning or machine learning is to be able to actually approximate these functions on the left, just given any old inputs, basically. And you can turn up the network depth. And it just kind of approximates a circle. So just while we're here, I'll talk about a couple of other things that we might go into in the future. So there's this thing called regularization, right? And in regularization, I'm going to apply a penalty for having basically a large sum of absolute values of parameters. That's what L1 regularization means. And basically, when I do this regularization, after it converges, you can see it's switched off essentially a whole bunch of inputs. And this is one way that you can start with a very large network. So it has all of this direction to go in when you're doing gradient descent. And then you can kind of eliminate a lot of redundant parameters afterwards, which is usually much better than starting with something that's too small. So you get these kind of unstable training things. And then, yeah, so you can play with some of these parameters up here, right? Learning rate is the size of the step you do at each gradient descent. And, you can try to classify other kinds of data, and it just seems to work. One other interesting thing I found out is, I think there was a question last lecture about why are neural networks sort of funnel shaped, like why are they big at one end and small at the other end? And this is kind of showing you why when they're reverse funnel shaped, they're not very good. So if you look at this, technically I have enough information here to have my good 7 neuron network, right? I just need these first 2 neurons to essentially act as the identity function or something like the identity function, send the information to the next ones, and then have them act the way that they did before. But they're not going well. And this kind of emphasizes that you need a lot of freedom in the first layer, less freedom in the second layer, and so on. Right, so I'll post this link on the website, and it's in the notes which are already on the website. Yeah, so the question is there any sort of guide as to how you should size your layers? Is that right? Like if the first layer is so big, then the second layer can be half as big maybe, or something like that? Are there any strict bounds? So I don't actually know. And I'm under the impression that finding the kind of ratios that work well is kind of an empirical thing. People apply it to this sort of data. This thing seems to work really well. Is there an explanation for why narrow then wide is worse than wide then narrow? So I think it's that idea of maybe deleting some information that you used to have, or just, kind of the first layer of perceptrons can move in almost any direction they want, but the further ones are kind of trapped as to how the first ones have moved. But honestly, I don't quite know. It's certainly something I've observed in practice and playing around with them, is that it's much better to have a bigger first layer and then smaller other layers. And it's mostly to do with this instability of training. So I have managed to train ones that are narrow and then wide, but sort of the number of times I have to attempt before something works is a lot higher. Yeah, so the question is in terms of computational time, what can you say about the width of the network or the length of the network or the learning rate? So I think the learning rate is meant to be something that is kind of balanced with the choice of initial conditions. And also, you kind of want a learning rate that's as high as possible without kind of, going off the deep end and overstepping where it should. And I think that's a little bit experimental, but I do think that you can kind of look at the speed at which the loss function's changing and kind of, pick a learning rate that's good. As for the width and the depth, so I've read somewhere that it seems like if you spend more nodes on depth, then you tend to get better models. So, you could have 2 depth 100 layers, or you could have one depth, sorry, two width 100 layers, or you could have one width like, 10 million layer or something. And these tend to have kind of like the same classification power. Those numbers are made up, but that's like the idea. Depth is worth more, but it's also like a bit harder to train, I think. Georg says it might be because of the training rather than the expressivity of the network. Like it's easier to train. Right, what's on here? This is just a little bit of a, what were you seeing on the previous page? So I told you that there's normally no activation function on the output. So on the website I was just on, it's actually using tan h as the activation function, which like maps every output into, between -1 and 1. And the loss function it's using is something like least squares. So he said that normally in classification problems, you want one of these like cross entropy loss things, but probably if you're just regressing a few points, it doesn't really matter either way. The next part of this is universality. And I guess the idea is, we want our neural networks to be able to approximate any function that we would want. So in that example of separating points with a circle, we want the neural networks to be able to approximate, something that takes value 1 outside a circle and 0 inside a circle. So the more precise question is, what kind of real valued functions on Rn can we get out of feed-forward networks with maybe just one hidden layer, right? If we can answer the question for one hidden layer, then, obviously we can get the same kind of functions for any number of hidden layers. So there are sort of umpteen results about this. I think the one with the nicest statement is this one in this paper of, that was released in 1993. I should mention, this depends on the activation function that you choose, of course. And it also depends on the width of the layer that you allow. So if I allow any width for my one hidden layer, then what kind of activation functions can I choose so that I can approximate any other function? I just have to choose an activation function that's not a polynomial, which seems like a little bit of a surprising result. So the first time I read this, I kind of thought, why does this implication of the theorem not contradict the Weierstrass approximation theorem? So if you remember, the Weierstrass approximation theorem says that if you have a compact set in Rn, then the space of polynomials is dense in the space of continuous functions on that set. So any continuous function on a compact set can be approximated arbitrarily well by a polynomial. So this just seemed to read to me like the wrong way around or something. Anyway, can anyone see the answer? Or rather, there's kind of like an easy proof of like, if sigma is a polynomial, why does this not work?
Wait, the degree is fixed. You're just saying linear combinations?
Yes, someone responded from the chat, I think. So Brian said the degree is fixed. So if sigma is degree k, then anything you get out of this set here is at most a degree k polynomial, right? So now you've become sort of trapped in this like finite dimensional vector space. And so you can't possibly be dense. So I did try to find a nice proof of this theorem. And this theorem is kind of provable if you replace the width with n. So in Rn, if you replace the depth with n. So in Rn, if I allow n hidden layers, then I can basically prove this theorem. But if in Rn I only allow one hidden layer, then it's sort of like 2 papers worth to like prove this theorem, as far as I could tell. And for those of you who are interested, like some of these conditions are not actually essential. So the activation function only needs to be continuous and locally bounded almost everywhere. And then you start getting like LP convergence and things like this. So this works on the LP spaces. And another remark.
What's so special about polynomials? Like, why are those the only bad ones?
Yeah, why are those the only bad ones? I don't exactly know what's so special about polynomials and why they're the only bad ones. I don't have a great answer to that question. I comment on the next slide that this like functions of this form are called ridge functions. Or something else. What are they? Plane waves. And these have been studied historically as like approximations to PDEs and ODEs and things. And these do have like some kind of intricate connection with like the geometry of the set you allow. Like if you change Rn here to be some kind of algebraic variety, then that like restricts the kind of solutions that you see. This might be down the wrong track though. So yeah, the other remark is that this says nothing about what width is required. You can kind of guess though, like if you guess that you're kind of constructing an approximation out of bump functions or something, and you have like a 1 Lipschitz function that you want to approximate, then the kind of width you need to get like epsilon precision is something like n to the minus epsilon, which is pretty bad. It seems that for deeper networks, you can get away with something much, much better than that, which is again one of these reasons why you might prefer deeper networks as opposed to just a shallow network. The question was, what was the takeaway from this slide? And yeah, the upshot is that as long as sigma is not a polynomial, then you can approximate anything you want. And if you think about the activation functions you might have seen, so there's like ReLU, there's like tan H, there's this sigmoid one, which is like 1 on 1 plus e to the minus x or something. Like these are all not polynomials. And for this reason, apparently. Yeah, so the question is, why do you use ReLU or tan H or something instead of just, you know, any other function? So I think tan H was used a lot because it's like a fairly simple sigmoidal function. This is back in sort of like the earlier literature from like say to like the 50s up to like the 90s and stuff. Once it became clear that like ReLU networks work very well, there is essentially no reason to calculate an expensive function at every step rather than calculating a very cheap function at every step. Right, so it's kind of like it takes a while to run tan H on a whole bunch of numbers, and it takes almost no time to just, you know, set a number to 0 if it's negative. As for why ReLU works so well, I think there are a few good explanations online, but I can't remember exactly why. If the activation function is almost polynomial, would the network train poorly? I think it depends on what you mean by almost polynomial. Like ReLU is kind of almost polynomial in that it's just 2 polynomials stitched together at a point, but it trains fairly well. So yeah, some of the discussion here is about like, why does ReLU work better than tan H? And like one of the things is that tan H flattens out, and so it has 0 gradient, and so you get nothing when you're trying to do backprop. Whereas for ReLU, it has this, you know, large piece where it has, you know, gradient, and so you can actually keep doing backpropagation on it for a long time. There's also something else you might come across if you're looking in the literature, which is called leaky ReLU. So leaky ReLU looks like, you know, y equals x over here, and then, oh no, you know, something that just goes down with like a very small gradient here. And this is for the same reason, because when, you know, in this region where you have very small gradient, you can still do some backpropagation rather than not being able to do any backpropagation. So this is leaky ReLU. But the fact that ReLU has like gradient for a long time is, yeah, for sure one of the reasons why it works well as a function, as an activation function compared to all of the sigmoidal functions that kind of flatten out towards infinity and flatten out towards minus infinity. Yeah, so a function that looks like this, you know, is not going to train as well as a ReLU, because you like can't see a lot of the gradient for a long time. You know, because it's fun, I might fire up this little example of how you can approximate some functions, you know, just for anyone who hasn't seen it before. So this is my ReLU here. So with my ReLU, I can create this function that we were talking about. And then with that function that we were talking about, I can make a bump. And something that Georg told me is that you really want the edges of the bump to go through a half, which was not obvious to me for some reason. So this is a bump, and you can make it as precise as you want. And you should kind of check that everything I'm doing here could be done in a single layer of a neural network. And then once you have your bump functions, you can take any function and you can basically just scatter these bump functions along this, right? And this gets you a reasonably good approximation to the function. You could narrow the width of these bumps and use more bumps if you wanted. That would obviously up the size of the layer that you needed to use, because the size of the sum that I'm using here is going to be kind of like the width of the layer. So this is kind of interesting for a constructive proof that you can do anything, at least in 1D. But I think it might be a bit misleading because I don't think it's how neural networks actually learn things, right? Neural networks don't actually make bump functions and then make other functions. They're kind of just finding this linear combination of these things called ridge functions. If you really wanted to go and look into the literature, you could go and have a look at that. And that might be a little bit more how neural networks actually learn things. Is there a reason that none of them are smooth? So there's a lot of activation functions are smooth. Yeah, so like hyperbolic tan is smooth. Yeah, so the question is, do the smooth and non-smooth functions affect the output in some way of what activation function you choose? I'm sure they affect the output a little bit, but I guess I'm sort of wandering into stuff that I don't know so well. What I have read is that from like a lot of experience, people have kind of settled on ReLU as being kind of like the standard activation function you should choose unless you have a really good reason not to. And I think part of it is also just due to the fact that it's so fast to apply. And like, if you can train your network like 1,000 times faster, that's probably worth having even a worse activation function if it were worse. So before the break, I wanted to comment on something that is not so much about maths or machine learning, but just about the stuff that you have to do machine learning. So this is about tensors. And the reason that I included this slide is because in the workshop last week, when I was trying to explain this, I got like a lot of blank looks. And I thought it might just be worth writing some of it down. So if you're a pure mathematician, forget most of what you know about tensors. Tensors are just multidimensional arrays of numbers if you're in this machine learning world, right? So you can index in multiple coordinates. So, a vector would be a 1 tensor because it has 1 coordinate you can index along. A matrix would be a 2 tensor. A block of stuff over here would be a 3 tensor. And these things here are called the shape of the tensor. Right, so this matrix is shape 3, 4. Right, and this is just telling you the extent of the dimensions. You'll also notice that this is kind of, should be the same shape as 1 NM. Right, there's as much data in a 1 NM tensor than there is in an NM tensor. But you will have to apply this isomorphism yourself if you're programming. Right, if you program something that's expecting a matrix and it gets something back with 3 coordinates, it's going to say, what are you doing? And you're going to have to, tell it which index to drop or something. So I might just explain some of the reason behind why we do this, which is that inside a computer, you essentially want to batch up numbers, pack them as close together as possible, and then run them through big bulk operations. And this just gets you, it doesn't sound like much. And in terms of big O complexity, it's not any different. But in terms of actual running time, it makes all the world of difference. And so here I've got an example of multiplying lots and lots of vectors. If I have a list of vectors, n vectors, and I want to calculate a matrix multiplication with each of those vectors, then kind of like if I loop through this in Python and calculate all of those products, that's going to be about a zillion times slower than packing them into a big matrix and just doing one matrix multiplication. So this is much faster. And this kind of is very relevant in machine learning because you need to go through lots and lots of iterations of these learning processes, right? Like how good your network is to some degree how much you can train it. Like this is why the really big companies like Google and Facebook and stuff have the best neural networks. It's just because they have the most computers to train them with. You know, they also have very good researchers and things, but to some degree, it's like how much data do you have to put into your network and how long can you train it for? So
the reason it's fast is because the matrix.
Yeah, that's right. Yeah, the reason is the matrix multiplication is optimized. That's why it's faster. And you know, Python is kind of like a slow language in comparison to what the matrix multiplications are written in. And there's all of this stuff to do with like, you know, locality of memory and things like that. Something you might see if you're dealing with tensors is tensor contraction. Yes, comment from Geordie, the deep learning revolution was an engineering revolution. So yeah, kind of the wild thing when you're programming is if you take a matrix and you program matrix multiplication, it goes at some speed. And if somebody who knows what they're doing kind of like rearranges your sums and rearranges things so that you're only going across part of the matrix in one way and stuff, they get a matrix multiplication that goes like 100 times faster, even though it's doing the same thing. And this is a bit why it's like an engineering revolution to do deep learning. It's because you need like a lot of computer smarts to be able to, you know, run tons and tons of data through the machine. Something you might see, which is cute, which you will be familiar with if you've seen like Einstein summation, is this thing called tensor contraction. This is basically just a generalization of the dot product or the matrix product, things like that, but you like will see it in PyTorch and things. Basically means like if you have two tensors, you can stick them together by doing something like the outer product of matrices. And then if you have two dimensions that are the same length, you can contract them and make them disappear by summing over them. If you think a little bit, this is exactly what the dot product is, or this is exactly what matrix multiplication is. Right, so where else do you see tensors? In image processing, you're going to see tensors that have large shapes just because, not even for like a data speed reason, but just for a data sanity reason, right? So you don't want to treat an image as a vector that's just like 1 million elements long. You want to remember the different dimensions of the image. So, you know, if you have an image, it has a whole bunch of pixels on it. And each of these pixels is a number, like a number between 0 and 255, or maybe a number between 0 and 1 if you normalize it. But it's going to end up being a 2 tensor with some width and height. Then if you move into color photography, you're going to need some color channels, right? So like standard color channels are RGB. And so you end up with, you know, this is normally 3. So you end up with a width, comma, height, comma, 3 tensor. And those 3 is, you know, 0 is red, 1 is blue, and 3 is green or something, 2 is green. And then at the point where you're trying to get all of your images stacked together so that you can batch put them into PyTorch or something, you might end up with a 4 tensor, where this thing here is just the index in my batch of photos. And yeah, I'm just saying this for the benefit of people following along the workshops, because a lot of the workshops have this kind of like, you know, there's kind of one line of code that fiddles around with tensor indices instead of like 10 lines of code that calculates something. So, you know, this kind of algebra of tensors you can get a lot done with, but it can be really intimidating to read if you don't know what's going on. And if you ever get stuck, you just start writing out the shapes and making sure they all work, and then you keep going through. So yes, programming this kind of stuff is annoying, but it's also extremely fast once you get it right. So, you know, if you're programming and it's saying, I want something of shape this, and you gave me something of shape this, then, you know, that's basically what everyone programming type PyTorch sees all the time. So don't give up. Was this example a bit more clear than last time with the matrix product thing? So there's a comment from Geordie that says that his idea is that there was a breakthrough and people realized that GPUs can run these things really well. Yeah, so for anyone interested, if you want like a slight mental model of how a GPU works, a CPU is very good at like following instructions, and it's very good at following conditional instructions based on, add this thing to this number. If that's less than 3, do this, otherwise do the other thing. GPUs don't have very many cores, right? They've got like 8 cores in your computer or something. CPUs don't have very many cores. GPUs have like 20,000 cores, but they're all really dumb. They've kind of got like one master controller that can follow out a fixed set of instructions. But if it ever has to say, if this is less than 3, then multiply this, otherwise do this, it kind of stalls and it has to do everything individually. But if it can stay in this kind of big batch mode, matrix multiply, you don't have to ask any ifs to do a matrix multiply. It can do tons of stuff in parallel. And this is kind of why GPUs run neural networks so well. Yeah, you can parallelize them across GPUs, but also GPUs internally are highly parallelized. One core might be controlling like 40 others that all load in different offsets into the same vector, and then they all perform the same operation and so on. It doesn't have to do it like one at a time, piecemeal. What is the main advantages of TPUs over GPUs? So the only tensor processing units that I know of are the ones that came out of Google in like 2016-ish. And these tensor processing units actually quantize information. So they don't even use like floating point numbers. They just use 8-bit numbers, like minus 127 to 128, or I think some of them even just use positive numbers. And like they found that this was enough for running neural networks. And therefore, if you can use all of your chip space just doing 8-bit numbers, then you can pack like 8 times as many numbers and operations in as you can from floating point. Like the chip space required to do, like standard integer arithmetic is also a lot smaller than floating point arithmetic. And so you can get even more on. That's my impression of what TPUs are. They're just more specialized than GPUs for this application. They're probably not good for regression problems though. You probably want floating point numbers for those. So in the second part of this talk, I'm going to talk about image recognition and convolutional neural networks, because these are one of the kind of giant success stories of neural networks. So, like Facebook can recognize faces and just like tell you who's in a photo. But this was kind of unimaginable 20 years ago. Like no one even knew of any algorithms that could do it. Right, and suddenly we can like train these neural networks and they just identify faces with like pretty good accuracy. And so on for classifying photos into like dog and not dog and things like that. So if you think of some of the difficulties involved in what we've seen so far. So a neural network, in what we've seen so far, which are fully connected layers, takes, you have an input, you have the first level of the neural network, and there's, every possible connection in there, right? You just have like a big matrix. So every possible thing is connected to every other possible thing. So first of all, if you have an image, that's a lot of data. And so that's just going to be a ton of parameters in your network. So it's going to be slow to run and even slower to train. Secondly is that, like in these pictures of cats I have here, this cat here looks very different as a vector from this cat here, right? And in a fully connected network, this cat here would be landing on entirely different perceptrons than this cat here, right? And there's like no reason why these perceptrons should treat these two cats as being the same. And then there's this cat up here, which is rotated again, which is another problem. And then there's this cat here, which I attempted to apply some kind of perspective transformation to, but I had to just redraw it myself because my iPad didn't do that. And then you can imagine there's some kind of threshold where if I squish a cat enough, you say, no, that's not a cat anymore. So some of the difficulties that arise in image recognition are the kind of symmetry of this space. And probably the main symmetry we'll be paying attention to is the translational symmetry. The rotational symmetries tend to be dealt with by other tricks. Like when you have an image, you rotate it like 7 different ways, and then you just send all of those into your network and see if anything happens. So those tend to be like a little bit more tricks. But also what we want to have a look at is that kind of neighboring pixels are meaningful, right? We have this like locality where, this pixel in the cat is quite close to these two. And there's nothing in our neural networks at the moment which is enforcing any sense of locality, right? This pixel over here could be linearly combined with like this pixel over here for no, at any weight we want. And yeah, so treating an image purely as a vector and having these fully connected layers is big, slow, and throws away a lot of this translational invariance or equivariance that we might want to have. And it's not just the translational invariance, it's really like the locality information between the pixels. Like in a normal vector, you don't say like, how close are like the third and fifth entries. Normally that's kind of like a meaningless question to ask. But if you know that your vector is like functions on Z or functions on R squared or something, then it is meaningful to ask, how close are these two values at these two close points? And that's kind of like, that's an example of the kind of data that we want to put in here. And if you're thinking of putting in any mathematical data that has structure, you might be thinking of similar problems. Right, so if you want to put a graph into a neural network, it again, well, there shouldn't really be relations between adjacent vertices on a graph, right? Say I put the graph into the network as like an adjacency matrix or something. This time I don't want these translational symmetries because that's kind of meaningless on a vertex set, but instead I want to permute things. Like I want my, whatever comes out to be invariant under permutations. It's not like vector or tensor because at the end of the day, they're just whole lists of numbers. But it's more like, knowing that the third and fourth elements of the vector are close and knowing that like the third and 30th elements of the vector are far away. And maybe, shouldn't even have any interaction. And with the fully connected layers at the moment, there's possibility for them to have interaction. Right, so basically the solution to this is very well known now. It's called a CNN or a convolutional neural network. So this is, as I said, wildly successful in machine learning at doing things that everyone wants to do. It makes sense over any domain that has some kind of grid topology or a group structure. So most obvious is images, but you also have 1D time series, right? Music, for example, has like locality between signals that are close together and none between signals that are far away. Bingo has locality. And the word convolutional neural network refers to both convolution and this thing called pooling together. It's very rare to see a convolutional neural network that does not have a pooling step. So we'll get to that later. But keep in mind that these are, these go together even though only one is in the name. And so for the purpose of image recognition, convolution is going to kill all of these birds with one stone. So in convolution, I'm essentially just choosing a very small parameter set, and then I'm kind of sliding that one parameter set across the whole image, which means that I'm treating the whole image uniformly. So like I said, we get less parameters out of these networks. We can treat the domain more uniformly. So we're treating a location over here similarly to a location over here. And the other thing we'll get to is it's more adaptable to differently sized inputs, which makes sense if you're Facebook and you want to send in like a whole bunch of randomly sized images into your network. Sort of everything we've seen so far is not set up for that. All right, so a quick reminder on what convolution is. It's got a nice symmetric formula and a less nice non-symmetric formula. And it's a thing you do to two functions. So here I've got two functions on the integers. Think of them as finitely supported functions if you want this to be nice. And their convolution is going to be another function on the integers. So right, just imagine this two very long vectors and I'm producing a third very long vector. The formula is what it is. We'll see what it looks like in another slide. Probably everyone here is familiar with it, but I'll just remind everyone. The thing to note is that it's using group structure. In this abelian group. This is kind of what it means to be a convolution, but that might be invisible if you've not had it pointed out before. So like kind of one of the inputs to convolution is what group are you trying to convolve on, which could be Z, or for images might be Z squared. Right, and this is kind of like a reason. This is like, I'm showing you some of the structure in the data and different ways to put it in. So if you have an abelian group and you want to represent locality, then maybe convolution is a good idea. So some exercises if you've never seen it before. It's symmetric. It's a linear map as long as you fix one of the entries. So the fixed one is normally called the kernel. And right, F maps to F convolved with that kernel is linear. So in some sense, it's just a big matrix. And it's also translation equivariant, but I'll show that in the next slide. I have this little warning up here. So cross correlation is what happens if I replace this formula with n plus m. You lose a couple of the symmetry properties of convolution, but otherwise it's basically the same thing. Right, and in the ML literature, people sort of use these formulas interchangeably. Right, it doesn't really matter. Your neural network will just convolve things and get something out that's like an image flipped, but it doesn't care. Right, so an example of calculating a convolution is, so you have a kernel, and the kernels that we're going to be seeing are all very like supported around 0. So you should just imagine like a little mask sitting around 0. So here's my mask here. And what I do is at this point 7 in the middle, I just take the average of my neighbors, right? So 5 plus 3 is 8 divided by 2, and I get 4, right? And then I kind of slide the kernel over to the right, and 7 plus 7, I get 7 out. 5 plus 8, 13 on 2. 7 plus 0, 7 on 2. 8 plus 0, 4. 0 plus, something. This is a bit of a question over here as to how we extend this, but just imagine that this is extended by zeros. So I get 0. And so this is like a really effective picture. When you're convolving with a fixed operator, you're kind of sliding this kernel over the thing, and then you're picking out features. And something I'd never connected in my head is that it's linear, right? So I should be able to represent this thing by a matrix. What matrix does this look like? Well, if I were to do the ones on the right over here, 1, 3 on 2, etc. Basically, it's a matrix that looks like the kernel repeated a bunch and shifted over. This is a straightforward observation, but this is just sometimes called like a Toeplitz matrix, or like a circulant matrix if your boundary conditions wrap around instead of extending by zeros or something. But you can see that this is sparse, right? And that's because my kernel is small. So if I get a small kernel, I have essentially a sparse matrix multiplication. Right, so let's go to 2D. So you can write down 2D convolution using the exact same formula, of course, because the convolution only actually depends on the group that you're putting in, which in this case is Z squared. Right, so I'm just imagining an image as a function on Z squared, so I don't have to worry about the boundaries right now. And then you write down the same formula. And then if you want it to be more explicit, you go and unpack what it means to convolve in Z squared, and you get a double summation down here. So if I haven't convinced you that convolution is the right tool for the job yet, hopefully this will. So I've got another demonstration here. So there's like a little example here of trying to convolve an image with this person's face. So you can kind of see that I'm selecting a little part, sliding this filter over. The filter is in the middle, or the filter is this matrix that you see here. And then I just calculate everything. So why is the convolution the right tool for the job? Basically, it picks out like this is already very well known to anyone that does signal processing, but like convolution with certain kernels can pick out features of an image. So in this one called right Sobel, I'm kind of picking out a lot of vertical lines. In this one called top Sobel, I'm picking out a lot of horizontal lines. And like, it's kind of impressive that I just have like a 3x3 kernel here that's already picking out a whole bunch of features from the image. Yeah, absolutely. So the question is there something in the kernel that determines what features come out? And yeah, the kernel exactly determines what kind of features come out. I guess like our interpretation of those features is like, you know, like I interpret this as picking out horizontal edges.
The question is how?
How? So if you look at like what this is doing, so it's kind of like a differentiation operator, right? I'm weighting the top positively, I'm weighting the bottom negatively, and that's kind of like calculating a derivative. It's a derivative that's happening at every point, and it's like a discrete derivative, but it's something like a derivative. So I'm looking at any sharply changing gradients, right? So if a gradient changes very fast, you know, I get a big response out of this kernel, and if it doesn't change very fast at all, I get like 0 out of this kernel. So like that's how all of the edge detection filters work, basically. Why 1, 2, 1 and not 1, 1, 1? You know, I think whoever wrote top Sobel decided that 1, 2, 1 was better. I don't know. But you know, like, oh, I'm on the wrong computer. I'm trying to, you know, I think we'd see kind of the same things if we did 1, 1, 1. Yeah. So, you know, to some degree, the exact values in the kernel don't matter so much, but, you know, this whole, like the shape of this kernel is essentially some kind of vertical differentiation. And, you know, there's other sort of cute things you can do. You can like emboss pictures and things like that. But the idea of these convolutional neural networks is instead to have a few of these kernels that are then trained by the network, right? So rather than having a matrix with a zillion entries and you can train each entry individually, what you're just doing is you're saying, okay, I'm going to have, you know, a 3x3 kernel and then try to train that. And one layer in your neural network will be a convolution and then like a ReLU. And this narrows down the amount of parameters that you have massively. It's also much faster to execute, right? You don't actually need to do a matrix multiplication. You just kind of do this like average of 9 pixels thing. So the question is, can you split up your image so you get like half one kernel and half the other? And actually the thing that you normally do is you say, I've got 100 kernels to train, and then you run all 100 kernels. And that's like one layer in your network. You might run them with some downsampling or something so you don't end up with too much data. But normally you're training a whole bunch of kernels in parallel. Right, so convolution by a small kernel is faster than a fully connected. And it's a huge reduction in parameters. Right, so if you have a huge reduction in parameters, you alleviate like a whole bunch of other things to do with like overfitting, having just, you know, something that's too slow to run, all of these things. So an example from this deep learning textbook, they're just saying in, you know, one case you can get like a neural network recognizing dogs pretty well, that uses, you know, 300,000 arithmetic operations per dog. Right, and this is using convolutional kernels. Whereas like a similar network in this like fully connected shape uses something like 8 billion arithmetic operations. So, you know, obviously you should prefer the smaller one if it does just as well. And I think, you know, once you get 8 billion parameters, you can't even train that. Like you don't know if it does as well because you just can't use it. Like the question is, you know, can you get a fully connected network, but then I think get a bunch of the entries like 0 or something and throw them away?
Like after you break and then check and then basically the threshold break, then you throw them away basically like that.
Yeah. Yeah. So if you keep doing this, like train a fully connected thing and then break them and then try to like trim off any things, like I think that could work. But like, you end up with like a general sparse matrix multiply instead of this convolutional thing, which is even faster. But the other thing is if you're starting with 8 billion parameters, you can't even put that really into a computer and do anything with it. So you can't even start. Yeah, I don't know if you'd typically look like something. I'm guessing not, because, convolutional networks tend to have, I don't know what the term is, but they're kind of matrices that are like 0, and then they have like a band of stuff down the center, rather than general sparse matrices, which are, like mostly 0, that can have things just in any spot. And so you won't necessarily get like the same locality. The other huge reason, which I was trying to explain here, was that like the reason to use convolutional networks is just because like convolution is such a good operation in like classic signal processing, at picking out features and stuff of signals. Why wouldn't you start with something that's proven to work like incredibly well? Right, so this is what I was saying before, which is that normally what you do is you say, I'm going to have k different kernels, and then I'm going to train them all at once. And the output of this layer is instead going to be, like k different images. So an image, as we said before, is normally a 3 tensor. So you're doing like convolution to each channel or something, and then you're doing k different convolutions, and so you get out k different images out the other end. So this is more data. So you somehow need to smush this data down, which is the job of pooling, which we'll describe later. Yeah, so there are many variants on standard convolution. So one of the things we didn't quite talk about is dealing with boundaries, right? So if I have this square filter and I'm dragging it along my image, I might get stuck in like the top left, but the final pixel that I'm computing is not the top left pixel. So I need to drag it off somehow. And you sort of have like a few choices. You can like imagine it living on z squared and extend by zeros. You could extend by ones, or you could just accept the fact that you're going to get a small image out the other end. So I think it's normally preferred to just extend by zeros. And part of the reason is you can make your network as deep as you like then. Because otherwise every time you convolve, you'll be like destroying bits of your image, and then you'll just end up with kind of like nothing out the other end to do anything to. Another thing that's done is downsampling the output. So this step is you say, I'm going to run a convolution, and then I'm just going to take like every 10th pixel. And if the network knows you're going to do that, it can just run like 100 times less convolutions. So that's one way of dealing with this sort of data explosion. Then you can also just forget about convolution entirely and just remember the locality, which is what this locally connected layers is. So locally connected layers says, rather than fully connected layers in my network, I'm going to forget about convolution for a sec. But maybe I'm just going to let this patch of pixels interact with this patch of pixels. And so you're kind of limiting the entries in your matrix that are allowed to be non-zero. And this is more general than convolution. Convolution is a special form of this. But this is what people can do, and this might be more relevant to your question, Jordan. Yeah, so the thing that you lose from this is that, so you still get locality of like, one pixel can't affect a pixel that's on the other side of the image, but you lose this uniform treatment of different parts of the image, right? Because the parameters that are here and the parameters that are, here don't necessarily have to be the same numbers. And then there's like this choice of initializing parameters. And this is again from signal processing. If we know a whole bunch of convolutional things that pick out features and images, just initialize some of our kernels to those, because why not? And they can kind of use that as a starting point, right? So if I've got like 10 kernels, I initialize the first 4 as like edge detection ones. I initialize the next few as some other well-known feature, and then they can kind of drive themselves from there. Right, so there's this last step that's pooling. And again, I think that part of the reason that this exists is dealing with the amount of data that's in images. And maybe I should draw a diagram first because I realize I'm missing this. So a convolutional network normally looks, something like this. You have an image coming in this end. You have a convolutional step. So stuff happens in here. There's kernels, there's like pooling, which I haven't told you about yet. But then out the other side of this, you just get like a vector in, like R100 or something. And then you run it through a few like fully connected layers. So this is generally what like an image recognition machine looks like. And there might be maybe many of these. So it could be like 5. But there's been some machine learning networks around at the moment that have like 1,000 convolutional layers. So you run them all through these convolutional layers, and then you've sort of like compressed the output into something out of the 100. And then the last step of the network is one of these more standard, fully connected layers. I don't have a reason as to why you would do things exactly this way, except for the fact that like, this is kind of like the feature extraction step. Right, so this is kind of like the step that's giving me my different nonlinear functions of the input. And then this is the recognition step. So this is normally how these networks look. I would say that convolution actually deals with locality more than translation. Like translation is, like convolution is translation equivariant, not translation invariant. Yeah. So like if I move the image over and convolve, it's the same thing as convolving and then moving the image over. It's not like after I've convolved, I can move my image in whatever way and I get the same output. So it's the pooling step that I'm about to tell you about that does that kind of invariance rather than equivariance. Yeah, I think convolution is much more of like a uniform treatment of inputs. Yeah, so here I'm telling you what the convolution stage looks like. So this whole part is called a convolutional stage of a convolutional network. Of one part only of that is convolution. Right, so we've described this convolution. This is where I have, my kernels. These are my parameters, K1, K, K. So these are the kernels that I'm training. Like part of the structure of the network is the fact that I've, specified the sizes of the kernels and specified that I have K of them, right? That's fixing my parameter set to train. That then goes through the detector stage, which is just another one of these ReLU things. Right, so you convolve to like say detect all the edges, and then in this example with the gradients, right, you're just picking out anything that had a big gradient and just killing anything that didn't. So that's the nonlinear step. And then you have this pooling stage, which is also often nonlinear. And what the pooling does is you break the image up into big chunks, and then you just apply some kind of aggregate function over that chunk. So that aggregate function might be max. Right, so like here in the red, like the max of all the stuff in here is 5. The max of all the stuff in here is 6. There are a lot of choices here. You don't necessarily need to compress your output here. You could, repeat the chunks as much as you wanted. But the idea is each pooling stage gives me a little bit of translational invariance. Right, so if I'm maxing or averaging over a whole bunch of inputs and I translate it a little bit, due to the translational equivariance of the convolution, right, the outputs are not going to change so much. And then hopefully the final output of the pooling step changes only like a very small amount. So this is kind of what's giving you the invariance. Right, so it adds invariance to these small translations. The other thing it does is it helps accept images of different sizes. I'll open Jordy's comments in a moment. So convolution, the other good thing about convolution as opposed to anything else is that it doesn't care what size image you have, right? My kernel can be like 20 by 20, and I can apply it to any image that's like larger than 20 or something. Right, so the convolution step can accept images of any size, but to feed them into my recognizer at the end, I really need to crush them down to some kind of uniform size. And so pooling can help with this. Right, so you can maybe rejig your pooling sizes a little bit depending on the image you were given in order to kind of uniformize the sizes. And this is how you can send in pictures of different sizes into these networks. So yeah, there is this emergent invariance that you sometimes get where networks happen to exhibit rotational invariance, but I kind of thought that this was due to the choice of data set that you trained it on. Like rather than training it on a whole bunch of upwards oriented cats, you like throw in a whole bunch of cats at weird angles, and the network kind of just learns to accept every kind of cat. Or there can be different networks for accepting different oriented cats, and you can kind of max pool them together or something. Yes, the convolution step right at the start is linear, definitely. But this detector part is nonlinear. Yeah, so I think the question is along the lines of like, why is this, like this looks like a short layer going into a big layer, and we saw that this was bad before, and why is it not bad here? I think that probably like filters like convolution are just the way that images are understood by a computer. The other thing is by having more and more convolutions, you can just have that not be so skinny at the front, right? So in terms of like, you just increase the number of convolution kernels you have, and that makes that that front layer like not so small. I'll just read this question of Jordan's. What differentiates this from having a single wide linear layer? So yeah, it's this nonlinear stage in here, and the pooling stage is also normally nonlinear. And so when you compose these things together, it's not just the same as having one big convolution or one big linear map or something. So the question is, should we be thinking that this whole thing in front of me is trained simultaneously? And I think that's what's often done. But there are like a million different variants where you can train something like this, figure out that like a couple of these convolutional filters it's come up with are like, providing like very big responses in the network. And then you can kind of port them to other networks and things. So like, I think exactly how to train a network is sort of like a whole kettle of fish. You really need to train it all at once because like it's only like right at the end here where like, this one is like the cat response, and this one is the dog response, and this one is the something else, bird. So like, how do you even train the first half of it without the second half? Like the first half doesn't know what it's aiming at through gradient descent. Like you really need to have these like categories coming out the other end if you want to train a filter to like recognize certain things. Again, like there are some beautiful pictures on the internet of people who have like taken out the kernels of these things and actually seen what they do to images. So I think there's something called like how neural nets see the world or something. And there's like some really like psychedelic pictures in there and stuff. Yeah, so can I get around with not training stuff at all? I think so. Like, I think, you could like another way to view convolution is just as one of these like different features that you give to your image. So like one different feature could just be like, I use this edge detection thing over my whole image, and then I take the average of that. And if it's bigger than 0.8, I report it, and otherwise it's a 0. And that gives like an incredibly strong indication of whether an image contains an edge. But that's like a filter that I've put in, right? In the same way that in that example, I was putting in like the x squared and the y squared things. Kind of the beauty of this is that the network can also just learn the convolutional kernel. But as I said, I think it's somewhat common to start them off, at least on a few pretty standard kernels.